Hey, welcome. Today, we are going on a serious quest. A quest to find the absolute coldest place in the entire universe. And trust me, our journey is going to take us from the deepest, darkest corners of space right back to our own backyard, uncovering a story that pushes the very limits of what we thought was possible.
So let's just dive right in. If I asked you, where's the coldest place in the universe? Where does your mind immediately go? What's the absolute rock bottom, end of the line temperature the cosmos has to offer?
You're probably thinking of the empty void between the stars, right? I mean, it makes perfect sense. It's a vacuum, there's pretty much nothing out there to generate any heat, so it's gotta be the coldest. That is a completely logical guess.
But here's the thing. It turns out even the deepest, darkest vacuum isn't at absolute zero. The entire universe, and I mean all of it, is soaked in this faint, leftover glow from the Big Bang. It's called the cosmic microwave background, and it acts like a universal space heater, warming everything up to a baseline of about 2.7 Kelvin. So that's 2.7 degrees above absolute zero. For the longest time, everyone figured that was it. 2.7 Kelvin was kind of the universal speed limit for cold. But, nature is full of surprises. Astronomers have actually found one very, very special place that breaks that rule. So, let me introduce you to the Boomerang Nebula. It's about 5,000 light years away, and what it is a young planetary nebula, which is really just a beautiful way of saying it's the aftermath of a dying star throwing off its outer layers. And this place, it holds the official title for the coldest natural spot in the known universe. Think about it this way. Almost everything else out there is being warmed up by that cosmic microwave background. But the Boomerang Nebula, sitting at a ridiculously chilly 1 Kelvin, is so cold, it actually does the opposite. It absorbs that background radiation, kind of creating this cosmic shadow. It is the only natural thing we've ever found that's colder than empty space itself. Which, of course, leads to the big question. How is that even possible? How does it manage to get colder than the background temperature of space? How does it become its own little cosmic refrigerator? Well, the physics behind it is actually something you've probably felt yourself. You know when you use one of those cans of compressed air to clean your keyboard and the can gets icy cold? That's a process called adiabatic expansion. When you let a compressed gas expand really, really fast, it loses energy and its temperature just plummets. And that's exactly what's happening at the Boomerang Nebula, just on a slightly bigger scale. You have this dying star at the center, blasting out gas at an unbelievable speed, 164 kilometers per second. That is just mind-bogglingly fast. And this hyper-fast expansion is what's actively ripping the heat out of the gas, driving its temperature all the way down to just 1 degree above absolute zero. So, there you have it, a natural wonder colder than the background hum of the universe itself. The Boomerang Nebula has to be the undisputed champion of cold, right? Case closed. Well, not so fast. As incredible as the Boomerang Nebula is, it's not even in the running for the top spot. The coldest places we know of aren't thousands of light years away. Nope, they're inside laboratories created by scientists right here on planet Earth. And this is where the story gets really wild. This brings us to a decades-long scientific race to achieve ultimate stillness, to create an entirely new state of matter, something that was first predicted by two geniuses, Satyendra Bose and Albert Einstein, way back in the 1920s. This bizarre state of matter is called a Bose-Einstein condensate, or a BEC. The theory was, if you could cool certain types of atoms, they're called bosons, down to just a tiny fraction of a degree above absolute zero, their weird quantum nature would completely take over. They'd stop behaving like individual little particles and would literally merge into one single, unified quantum object, a superatom. See, at the quantum level, everything acts like both a particle and a wave. So you can picture hot atoms like a bunch of tiny billiard balls bouncing around randomly. But as you cool them way, way down, their wave-like nature starts to dominate. Their individual waves get bigger and start to spread out. And then, at these insane temperatures, those waves overlap and fuse into one single coherent wave. They become one thing. So just how cold are we talking about here? Let's get some perspective. The universe's background radiation is 2.7 Kelvin. The Boomerang Nebula is an impressive 1 Kelvin. The very first successful Bose-Einstein condensate made back in 1995 reached 170 nanokelvin. That's not millions. That's billions of a degree above absolute zero. We're talking millions of times colder than the coldest place in nature. And 1995 was just this incredible, historic year for physics. It was a genuine race. On June 5th, Eric Cornell and Carl Wyman's team in Colorado got there first, using rubidium atoms. Just a little over a month later, Randall Hewlett's team at Rice University did it with lithium. Then, by September, Wolfgang Ketterle's group at MIT had made one with sodium. It was just this breathtaking cascade of breakthroughs. And what made the Rice team's achievement so amazing is that they used lithium atoms, which actually attract each other. As Randall Hewlett himself said, a lot of physicists thought that this natural attraction would make the whole group of atoms just collapse in on itself before it could ever form a condensate. Proving them wrong opened up a whole new world of research.
Okay, this all raises a really important question. Why? Why go to all this unbelievable trouble to make something so ridiculously cold? What's the point? How does a mind-bending physics experiment actually matter in the real world?
It's because these super atoms are exquisitely sensitive to the world around them. Using a technique called atom interferometry, scientists can use them to measure things like gravity with a precision we've never seen before. This could lead to things like navigation systems for spacecraft that never get lost, or even devices that can map tiny gravitational changes to find hidden tunnels or water reserves deep underground.
But really, the ultimate prize here is knowledge. A Bose-Einstein condensate is like putting the quantum world under a giant magnifying glass. It lets physicists see and poke and prod quantum behaviors, these bizarre rules that usually only apply to tiny subatomic particles on a scale that's big enough to actually study. It lets us test the fundamental rules that make our reality tick.
So we've gone from the faint warmth of the Big Bang to the freezing breath of a dying star, and all the way back to a lab on Earth, where human curiosity created temperatures millions of times colder than anything nature has ever cooked up. It really makes you wonder, doesn't it? Now that we can forge states of matter that people once said were impossible, what's next? What other impossible things are we going to create?